All right, line A1, learning task 17. We're going to take a look at capacitors in AC. And as we said with the with the inductors in AC, we need to be very careful about the way we look at these circuits. If we are dealing with AC, there's going to be some similarities. We're still going to use our base theory to analyze them, but there's going to be a different reaction that's going to go and happen. And the heart of this whole reaction is going to be, once again, what does a capacitor do? A capacitor opposes a change in voltage by using current. Okay, that's our short description of what a capacitor itself is supposed to do. It's going to oppose a change in voltage by using current. Once again, the key words for us to go and highlight in this is this word change. Anytime that the voltage is changing, we are obviously now going to go and get opposition out of the capacitor. Well, we're dealing with AC, which means that we've got a constantly changing waveform, which means we're going to have a constant opposition. What is that opposition going to be? Well, that opposition is going to be done through the use of current. So we're always going to go and have a current that is going to be opposing our main current that we would otherwise have. Let's examine these things once again, starting from a theoretical standpoint. We haven't gotten to the practical inductors and capacitors yet, but looking at a theoretical AC circuit that only has a capacitor inside there, we would know that once again we'd have to satisfy Kirchhoff's voltage law. When the switch would go and close, whatever I'm dropping for volts over here is going to have to be equal to whatever I am sourcing for volts that I'm going to go and have over there. And if I take a look at that, I know that V for a capacitor is equal to my Q over top of my C. In other words, my capacitance, that's going to be a physical build, 8.85 times 10 to the negative 12 times K times A over top of my little d. All of that is going to go and define physically how a capacitor is built. But Q is the finite number of electrons that have accumulated on it. So anytime that my voltage source is going to be at a peak, I must also have a peak of coulombs of charge that I'm going to go and have off of that as well in order to go and match that so that I can go and have that voltage, that opposition to voltage, or that dropping of our voltage across there. Anytime that my voltage is dropping, I'm also going to be releasing electrons off of the plates to go and drop my V, because the only way for me to drop the V is to be dropping the total coulombs of charge that I'm going to have on it. They show all of this on this graph right over here. Once again, let's just put that formula up top over there. V is equal to Q over top of C, the amount of charge over top of the amount of coulombs that I'm going to go and have. What we're seeing over here is that we're filling the plate up. So from 0 to 90 degrees over here, I have got a capacitor, and I'll just draw it. I'm drawing a polarized one just because we're used to seeing those right now, but it's AC, so we wouldn't be using the polarized kind there. But what I'm seeing is that the amount of current going into the capacitor is dropping. The reason that the amount of current that's going into the capacitor is dropping is because I'm filling that plate up, right? As I fill that plate fuller and fuller and fuller, there's less and less room for current to go and flow in. This I that we're looking at is the current flow to and from the capacitor. To and from the capacitor itself. So I see that as my voltage rises to its absolute peak, I'm going to store the maximum number of electrons on there, and my current, the amount of electrons moving through the lines, is going to drop down to 0 right when I hit the peak. At that point, my voltage is going to go and start to drop back away. And if my voltage starts to go and drop back away, that means that I'm going to be relaxing the distortion that I have on my orbitals, which means that I'm no longer going to have as strong of an electrostatic force to go and hold onto my electrons over here. And so some of these electrons that were stored over here on the plate when I hit that peak are now going to start to drift back out over here. So I'm going to have electrons that are now going to start to slowly drift out. And then as my voltage drops more and more rapidly, they're going to go and more rapidly leave. Take a look at our current. Our current is going in the opposite direction, right? The voltage is dropping, and now our current has reversed its direction. My current is going to go and reverse its direction. Then I'm going to hit the point where I've got no source voltage, so I've got nothing that is holding these electrons on there anymore. And so the rest of my electrons are now going to be whoosh, just flying off of that thing. what I'm going to be doing is I'm going to be running through my circuit, through my source, back up to the top side over here, and I'm going to be building my electrons on the other side. So now my voltage is going to start rising in the opposite direction. As my voltage rises in the opposite direction, my amount of charge, my coulombs, right, this whole area here, the number of electrons that I'm going to start building on this side is going to go and be building. Erase those ones over there. And I'm going to go and see my line current dropping away to a value of 0 by the time that I completely fill up the plates, get the full Coulomb charge all the way on top of here. Once again then, our voltage is going to go and decrease in the opposite direction. As it decreases in the opposite direction, then these electrons are going to be able to go and move back around in the opposite direction. And so I see that over here, as that voltage decreases, now my electrons move into the positive ground. My current changes its direction. Once again, this graph that we have over here is a stabilized system. I should have mentioned that probably right at the beginning. The book never mentions it, but if this is the very first time that we were charging up a capacitor, we're going to go and have a bump of current, and then it's going to go and stabilize into this system that we're seeing over here. So this is a stabilized system that we are looking at. Is it very similar to the way that we analyze the inductor? Absolutely, it's very similar to the way we analyze the inductor. The big difference is that now this is crossing here, and this is crossing right over here, which means that we have got current that crosses the x-axis before my voltage crosses the x-axis. And so what we're going to go and say is that my current must be leading the voltage. It's doing something, and then the voltage is copying it, but the voltage is later that it's going to be copying. So my current leads the voltage. What we use for this is we use the mnemonic ICE. Okay? ICE, ICE, baby, ICE. Current, my amps. We use an I to represent that. C represents capacitance. E represents my volts that I'm going to go and have over here. So when we're looking at inductance and capacitance, we see that they're going to be opposite, right? Remember what we said for inductance? We said Eli, right? Eli, L, Eli, like that. Where my volts lead my current, now for my capacitors, my current leads my voltage. Remember, for every action, there's an equal and opposite reaction. Our inductor is basically just doing the exact opposite of what our capacitor is doing. So we'll be able to use these to counterbalance each other later on, and we'll get into that, when and how and why we do some of that counterbalancing. For now, let's go back to this over here, the fact that we've got this leading current, and let's go and represent that graphically. We can do that through a use of vectors. These are vectors off of an AC system. All vectors on an AC system are actually phasors because the AC goes through 360 degrees. Once again, we are going to go and start with our reference vector on 0 over here. That's going to be my voltage. And then I'm going to go and put my current into the top side over here because we know that current leads the voltage for anything that is going to be purely capacitive. Like our inductor, we have opposition. We don't just have current that's just flying into that system and going wherever it wants at a completely unrestricted value. Our current is going to be restricted by the electrostatic fields, by basically how much, let's go all the way over to here, the thing that's restricting our current is going to be the electrostatic fields and how many electrons we can stuff onto these, right? Those electrostatic fields around each one of these are preventing us from stuffing more and more of these onto there. So we need, once again, a way to go and quantify that. Like we did for the inductors, we're going to go and use this form of opposition that we are going to go and call our XC. This is going to be my capacitive reactance. And it's going to be the same as ohms in that it's going to go and oppose the flow of current. And it's also going to be measured off of it's also going to go and utilize the ohm symbol in all of my measurements. This XC is going to be affected the exact same way that my inductance is. Remember, these are just flip sides of the same coin. Frequency and the physical value. Voltage will not go and affect this. We know that V is equal to Q over top of C. If I increase my value of voltage, it's just going to go and increase the number of electrons that I'm going to stuff onto that plate. It does nothing to the actual capacitance itself. But my frequency and my capacitance themselves are going to go and do something. If I go and have, I'll go back to this one over here, V, Q, and C. If I were to go and have, increase the frequency. So double my frequencies. Now I've got twice as fast of a waveform. I've only got half the time to stuff coulombs onto there, which means that I'm going to go and have half the amount of frequency, or half the amount of charge that's going to be built up on here, which would mean that my voltage would be seen as being lower. And if my voltage is seen as being lower, that means that I'm going to go and have a difference in my current there as well. It's going to be an inverse proportionality. Same with my capacitance, the actual capacitance itself, as that goes up and down. As I create more room on the plate or less room on the plate, it is going to go and affect this XC. And we tie it all together into this one formula that we have over here, which is going to be XC is equal to 1 over top of 2 pi FC. Wait a freaking minute. Where have we seen this before? Well, we have seen the 2 pi F inside of our inductance, only it was on the top side of our formula. Now we're putting it on the bottom side of our formula because we're opposites, and we're putting it in with AC. I want just to compare this real quick with my XL. XL is equal to 1 over top of, getting ahead of myself, is equal to 2 pi FC over top of 1, right? Anytime that we've got a formula, we can put it over top of 1. I see that these two are flip sides of the same sort of coin over here. Once again, dealing with our capacitive reactance, since that's what this one's all about over here. My capacitive reactance, what I'll note about it is that I'm using this 2 pi inside there, which is going to be my radian description of a circle. So it's going to be my total capacitive reactance over top of 360 degrees that I'm going to go and have. The rest, the frequency, and the C, the capacitance. Frequency is going to be measured in hertz. Capacitance is going to be measured in my farads. Let's look at these graphs that we are going to have over here. Now we have got, I don't want you to go and take a look at this one here yet. We'll compare that one in a second. We've got figure number 4 over here, which is power, voltage, and current inside of a purely capacitive circuit. We know that our current, they're no longer showing us the coulombs, but we know that our current is going to be leading my voltage through here. And if I go and multiply these together, a positive current and a positive voltage, I see that I'm going to go and get a positive power. And over here, I got a positive voltage and a negative current. Positive times a negative gets me a negative power. And then over here, I'm going to go and have a negative current, negative voltage. Therefore, I'm going to go and have a positive power. And then over here, I'm going to go and have a positive current, negative voltage. And so therefore, it's going to be a negative amount of power. What you see coming out of this thing is that we have got a frequency waveform, same as the inductive one, that is going to be double the frequency of my base, and it's also going to be doing that same stupid thing where it's taking power and then dumping it back in, taking power and dumping it back in. Generally speaking, this is seen as being a waste of time, to go and take something out and put it back in. We used that bank analogy, bank deposit analogy in the previous video. It is not something we desire to go and see. However, it does have its uses in certain situations. We'll cover those situations later on. Let's start, though, for now, by labeling what this is going to be called. We're going to call this thing VARS C, volt amp reactance C, also known as wattless power, also known as quadrature power that we are going to go and have. What I also want to point out about it is it starts in this top quadrant, in this positive quadrant over here. Let's take a look at this other graph. This other graph over here was my inductive graph, right? From the previous, when we were looking at these things in AC. I note that for the same AC voltage, okay, that's this E over here. Yeah, they're a little bit wider and stuff, but we see that the voltage first goes into the positive. I see that for my capacitance, it starts out by taking power. I see for my inductance, it starts out by giving power. And then when my capacitance starts giving power back in, that's when my inductance is going to start to take power. And so what we're going to be able to do with these systems is we're actually able to go and place them into the same circuit. And so then I can go and get these two to interact. When that one's taking power, this one's giving power. When that one's taking power, this one's going to be giving power, etc. We'll use them as a cancellation, a form of cancellation, so that we can go and take out that whole concept of, wasted power that's passing back and forth. It's basically like, if we go back to that bank teller analogy, it's basically like if the bank teller just put somebody, at the door and they said, hey, you just deal with this person that wants to go and, pass stuff back and forth, but they don't actually do it through the bank system. They just pretend like it's going through the bank system and it's on the outside. The bank isn't affected. You're still happy because you're doing deposit withdrawal, or you think you're doing deposit withdrawal, but it's not actually making any difference to the system. It's actually a terrible analogy now that I think about it. I'll come up with something better. Maybe by the time that we get around to class, I'll have a better analogy. I don't know. Sometimes I have to make these things up on the go as I'm going along. Nevertheless, whatever we come up with later on for that, the analogy of how they're canceling each other out, or not the analogy, but the truth of how they cancel each other out, that my vars C, my leading vars, are able to cancel out my lagging vars, is going to become very critical to us as we start going through all of our capacitive and inductive power factor correction later on. Last of all, we're just going to talk about this reactive power that they have. They give us a formula for reactive power, volts times amps times my sine theta. Sine is always going to be my opposite over top of my hypotenuse that I'm going to go and have. So for most triangles, if this was going to be my theta, this would be my hypotenuse. Hypotenuse over here. Hypotenuse over here. This is my opposite side over here. The opposite side is going to be where I'm going to always have my x's. XLs, XCs are always on that far side of that triangle. Hypotenuse is going to go and be my impedances. We use this sine of my angle over here to go and figure out what I have got for. Now, if I've got a completely leading circuit, a purely capacitive circuit, then I'm going to go and have a value of 1, because the sine of 90 is equal to 1. Punch in your calculator. Take a look if you don't believe me. It's going to come out as a value of number 1, so my total amount of power, if all I have in the circuit is capacitive, all of my power is going to be reactive power. We'll see a bunch of that in the next learning task, which is going to be calculations once again. All right, let's go over to that one next.